To another short theorem from probability theory. We're going to be talking about the distribution function, random variable, and probability space comradeship theorem, because I wasn't sure what to call this. Right. So, what's the claim? Well, let f be a function, a real function between, from the real number line onto the real number line, and let be a function satisfying the axioms of a distribution function. Well, they're not really axioms, more like characteristics. Namely that it is non-decreasing, it is, the right-hand side limit exists everywhere, and it is, the right-hand side limit exists everywhere, and the left-hand side limit on the interval it is defined on is 0, and the right-hand side interval it is defined. The right-hand side limit of the interval it is defined on is 1, right? So let it be a function satisfying these three axioms, say. Then there exists a probability space omega script A and P and a random variable x which maps omega script A into the set of the real numbers and the Borel sets on the real numbers, such that f is actually equal to the distribution function of the random variable x. Right. The proof is very simple. Look, we know, from measure theory, we already know there exists a measure mu called the Lebesgue-Stieltjes measure whose distribution function is f. Is precisely f. Right. By definition, this means that mu, that's our Lebesgue-Stieltjes measure, let's call it mu. Mu of the negative infinity to a semi-closed interval is equal to f of a for all real numbers. Right. Okay. Well, we have found f of x, because we can simply put f of x. Well, pardon me, fx equal to mu of the interval negative infinity to, say, a. Right. All right. But we still need to find the probability space and the random variable. Well, all right. Now we have many choices, really, but we'll go with the simplest option. Put the probability space equal to the most basic one. So we have real numbers, the Borel sets on the real numbers, and the measure mu we have already found. That's the Lebesgue-Stieltjes measure. And put the random variable of x, because x now is a real number, as x, right, for all x, which is precisely what we wanted. And thus we conclude the proof.